Okay, so this one I think is going to be a shorter run than the last 40-minute video. It's kind of long. Maybe I should make shorter, more digestible videos. I don't know. You tell me. What do you want? But I sort of gave the impression, and in fact, I was even under the impression at the beginning of last video that the definition of an adjunction required both the unit and co-unit. But in fact, I'm going to prove to you today that if you have just one of them, this defines an adjunction. And we're actually going to use this, I think, in the next video. So it's a handy little fact. So basically recall that a unit, so I've got some categories, C and D, and I'm supposing that F is left adjoint to G. And so one of the ways of saying that was that I had a natural transformation, which we called the unit, from the identity functor to F composed with G, such that for all maps from X to GY, then there exists a unique map going from F of X to Y, which I'll call H, such that the diagram, so we have X, A to X it's a natural transformation. So in particular, it gives us a morphism from X to GF of X. And because H goes from F of X to Y, I can apply G to that map. And yeah, so I've got this unique H that makes this diagram commute. Okay, we'll probably be referring to this a bunch over the course of the video. And last time we talked, and then there's also the co-unit. So I'm not going to go through everything defining the co-unit. You can look at the last video, but that instead goes from, that's a natural transformation from G first, then F to the identity functor of the category D. Okay. So now I didn't write the rest of the conditions because I'm not going to verify that part of it, but I will tell you how to construct the this natural transformation, the co-unit, if you have a unit, right? And so in order to do that, well, what do I need to show you? So because this is a natural transformation, right? I should give you a collection of maps, a collection of map attached to each object Y of my category, such that for every morphism in my category, I get a commuting diagram where this is FG of G of FG of Y prime, and these go down to Y and Y prime, and I have a morphism here. So this would be my, map determined by these things, right? And so this diagram commutes. So if I can show you this, then well, that's me constructing the natural transformation epsilon. And then, of course, you would need to verify that it satisfies basically the dual of this picture over here, the co-unit diagram. But, again, as usual, I'll leave that to you. If you ask me nicely in the comments, maybe I'll make a video going through those details. So, okay, how are we going to do this? Well, first, let me define over here. So what I'm going to do in this box, so somehow I've got to use eta to construct this, right? So if I take X to be GY, for some fixed y, right? And so I've got gy down here, and this is going to be g of f of g of y. So this will be eta sub g of y. And I'm going to choose here, right? So the arrow that I choose goes between these two objects, right? From my x, right? X is this thing here. I'm going to choose the identity arrow between these two objects. And then once I've chosen that arrow, well, by the defining property, I know that there has to exist some arrow that goes from f of x. So in that case, this arrow, which suggestively I'm going to call epsilon sub y, in this case is going from f of gy to y, right? There's a unique arrow such that when I apply g, this diagram commutes. Okay, so that already gives me part of the definition of the natural transformation, right? So for a natural transformation between these functors, the first step is to tell you the data of a morphism for every possible choice of object. Great. But now what I need to do is to convince you that for every possible choice of morphism between these objects, that I get a unique, what's a color? I don't know. I haven't used orange in a while. So I basically need to construct this diagram, right? I need to convince you that there's a commuting diagram of this sort. So suppose, of course, we've got our g from y to y, and I need to prove that this diagram here commutes. Well, how am I going to do that? Basically, what I'm going to do is I'm going to construct a map H between these two things. So I'm just telling you the idea of a proof. I'm going to construct a map H between these two objects using eta, right? So in particular, I'll have some H with unique properties, making some triangle like this commute. And then I'm going to show that, well, H, I'll separately show that the applying G to this composition also satisfies that, and applying G to this composition also satisfies that. And then I can conclude from my, defining uniqueness result that, well, both of these underlying maps in here, they had to be equal maps all along. So these will be the same map. Okay, so that's the idea. Let's get into it. So I have some notes here, of course, because I got myself very confused about all of these diagrams. So we start off, right? We've got our choice of G, goes from Y to Y prime. I can apply my functor G, and so that gives me a map here, right? And now, just like I did before in remember the definition of epsilon sub y, I basically just took this diagram and I plugged in x for gy. I'm going to do the same thing again, except instead of the identity map here, I'm going to have big G applied to little g, right? So now I know that there exists a unique map, H, I'm going to call it, which goes from GF of GY to G Y prime. Sorry. Ooh, I forgot to put a prime down here. Hopefully that wasn't too confusing. Which makes this diagram commute. So here we have GF, G, Y. Oh, I think I had one. Sorry, and that G shouldn't be there either. So confusing. So this is G of H here. Right. Okay. So there's a unique H making that diagram commute. Fantastic. So that's the H above I said that I was going to grab. Okay, so now, well, we have this map. We have G composed with eta sub y. So if you remember this commuting diagram above that I'm trying to show, right? So I'm gonna apply G to the composition of these two things and use the defining properties to show that that has to be H. So this is indeed, if you track where these things are coming from, this goes from FG y to y prime. But by the defining diagram of epsilon y, right? We go back up here, we look at this diagram that defined it, written out symbolically. That diagram says that the identity on G sub y is G of epsilon sub y composed with eta sub G of y. And then that means that, well, if I apply, so I go G, applied to G composed with epsilon sub y. Well, G is a functor, so it respects composition. Sorry. And here I'm going to squish in. Sorry, here should be G G sub y, right? Because basically what I'm doing, I'm looking back at this diagram up here. And I want, right, G of my composition is basically, I'm going to show that this arrow makes the diagram commute. So I want to show that after composing with this, I get the identity on G sub y. Right. Okay. So I have eta sub G sub y here. But now you can see from this, right, that gives me this part. And so this is just G sub G composed with one GY. And in other words, that's G at G. But that's exactly what I wanted to show, right? I wanted to show that if I did eta sub G sub Y, and then I applied G of this composition, that then I got G of G, right? That's exactly, again, this which defining diagram. Sorry. That's this defining diagram over here, right? Yes, right. This is going around in this direction, and I was able to conclude that it's equal to G of G, which is the other arrow here. So what does that mean? By the uniqueness of H, I conclude that G composed with epsilon sub y is equal to H. Okay. That's one part of the diagram. For the other, we're going to use the fact that eta is a natural transformation. So because eta is a natural transformation, we get the following diagram. Just bear with me for a second. So this is eta sub G sub y, F G, G F G y. Here I've got G of G going to G y prime. And over here I have eta G y prime, G F G y prime, G, and this is GF of G, which, by the way, is the same thing as G of F of G at G, right? So where does this diagram come from? Remember that eta is a functor from the identity on C, rather, to G, F. So F first and then G. So this is just unpacking what it means to be a natural transformation in the context of this map G, or rather, really what I'm doing is I'm plugging in, I'm taking my map G, I'm applying the functor big G to get this map, and then I'm plugging this thing into the defining feature of this natural transformation. So that means that I get this commuting square. Oof. And then by the definition, so by the definition of epsilon sub y prime, which I didn't write out explicitly, but if I scroll back up here, right, remember how we defined epsilon sub y, so that works for all y, including y prime, right? Well, I'm going to draw the diagram now. We also get a commuting diagram, right? Epsilon sub y prime is the unique thing which makes this lower diagram commute here. Right? That's by definition. Well, the diagram above commutes, the diagram below commutes. So if you jam some commuting diagrams together, everything should commute. If you're not happy with that explanation, you can go ahead and check the compositions of maps step by step on your own. But the takeaway is that basically I'm going to squish this diagram together, right? So I'm just going to do this composition and call it all one big arrow. So maybe I'll write it in orange. Well, really, once I do that composition, I just get G of G, right? So I'm going to have GY. Going down, here is G of G, G of Y prime. And over here, I'll have GF of GY. And that goes over here. So that's still just going to be this arrow. So that is eta GY. And then I have, just this arrow here, right? But what is that arrow there? Let me write it out a little bit more fully. The thing that goes there is G epsilon sub y prime composed with G of F G G, but that is G of some arrow, right? And remember that when we set up this diagram, this is the diagram that defined whatever our H was, right? So that means, and remember, H was the unique map such that when we applied G, this diagram commutes. And so we're forced to conclude by the uniqueness that whatever that map H is the same as if we composed these two things. But remember, if I scroll up a little bit, right, we also saw that H was G composed with epsilon sub y. And that basically gives us the results, right? So the fact that the far left and the far right are equal. Some joke about apoliticism, horseshoe theory, centrism to be found there. That is exactly what we needed to prove that this diagram commutes. And remember that that was the defining feature for the family of maps epsilon to define a natural transformation. Okay, so I will leave it to you to think about why epsilon satisfies the counit property. But as you might guess, I mean, it's essentially you're leveraging the uniqueness results from Ada that we use to construct epsilon in order to get the uniqueness results that you want. So maybe you found all of this very abstract compared to the intuitive beginning of the series. In the next video, we're going to dive off into even deeper abstraction. But in a video or two after that, I will try and bring things down to earth. But I wanted to go all the way out because, you know, people ask limits, and I wanted to really properly connect the most hoity-toity version of limits to the down-to-earth, you know, definition of stocks, of sheaves that we deal with. So that's all, and I'll see you in the next video.